is if we consider a reaction that shows stoichiometry of proton transfer. Okay. Our proton here being a hydrogen ion, okay, or H+. We could write this sort of basic reaction as A plus B is going to C plus X is some stoichiometric equivalent needed, or however many of our protons are moving. And the Nernst equation for this reaction would be given by delta E is equal to standard state delta E minus RT, the natural log, over BF, the natural log of C, H plus, A, and B. And at standard state, by definition, we said we would let A and B, our standard state A, our standard state B, our standard state C, would all be equal to 1 molar. Okay. Remember that a real equilibrium constant or a real reaction quotient, they all look like this. They're all divided by 1. And we just aren't showing any of the bottom terms. All the 1 molars are dropping out. Okay. And we're going to let the standard state concentration of hydrogen ions of our protons be equal to 10 to the negative 7th. Why do we think that is? What are protons related to in the body? What's the concentration of hydrogen ions related to in the body? And what do we need the pH of the body to be? 7, okay? This right here is for biochemical standard state. Okay. So pH is equal to the negative log of the concentration of hydrogen ions. If we let this be 1 molar, then pH would be equal to the negative log of 1, which would be equal, we'd have a pH of 0 if we let standard state pH be 1. Okay. I'm sorry, the standard state concentration of our protons also be 1 like everything else, then pH would be 0, which doesn't make sense. So we let pH be equal to the negative log of 10 to the negative 7th, gives us a pH of 7. Okay. So here is our standard state concentration of protons. Okay. And this is denoted, biochemical standard state is denoted with a prime sort of notation that looks like this in your book and in the tables. There's a short proof. There's a proof that I'm not going to go through on page 431 of your book that basically sets up this. Biochemical standard state potential difference is equal to the standard state potential difference plus 0.414 times whatever stoichiometric amount of protons you're moving divided by nu, which was our electrons. Okay? I don't have that related. This is not on the equation sheet. I'm not going to ask you to use it. Read it if you're interested. What this ultimately does is this is an estimation of changes in potential as a function of pH. And we're going to look at table 11.2 again. That was for all of our biological redox reactions. And what we'll see is we'll notice the prime. We'll notice those are given for biological pH. And then when it populates on the bottom and it has the iron for that same sort of iron reaction when we were talking about standard state, that's because pH was considered 0. Now we're considering it 7, and that's why those numbers are different. So the definition of our standard reduction potential, again, a parameter that determines which direction electrons flow in a coupled redox reaction. It's a measure of a tendency to want to be reduced. What you can see here, so up at the top, standard reduction potentials or electrode potentials with respect to the hydrogen electrode, okay, with respect to hydrogen as our standard, pH is equal to 0. Okay? And so that's sort of all notated here. Like we said, these ones get reduced. I mean, anything higher up wants to get reduced if you have to compare between two negative or two positive values. This was our 11.2 is our biochemical or our biological redox reactions. Again, they're all written as reduction half reactions. Okay? And then notice there's a prime now on here because we're talking about pH 7. And what I was showing you here was that cytochrome C, its actual active site, the site in cytochrome C that's participating in a biological redox reaction happens to just be an iron ion. Okay? And so here we have this iron ion with like a 3+ charge is being reduced. It's taking up an electron and going to 2+, and that has a 0.235 volt standard biochemical standard state potential. From table 11.1, this exact same reaction, where we're just looking at the reduction of this iron ion, has a different value, and it's because pH was different. This table's for pH 0. This table, it's ultimately just the same thing. It's only talking about what's going on with the iron, but now we're at pH 7. I think this announcement was about some other reminders. Okay? As you can see, after I gave this lecture last time, I had to announce a whole bunch of things on Canvas to clarify problems. So I'm trying to solve them now in advance of, between now and the next exam. So this is important, though, just to recall. We do not include the concentration of water, okay, in our setting up our equilibrium constants or setting up our reaction quotients because we let biochemical standard state concentration of water be 55 molar. And what we're saying is these millimolar concentrations of other stuff changing, whatever it is, are not ultimately affecting the overall concentration of water significantly enough. We just let this ratio of water be 55 molar. It's 55 molar the whole time it's participating in the reaction. The standard state is 55 molar. It drops out. Okay? It's just equal to 1. We don't need for water 55 over 55 is 1. For proton concentration is sort of another special situation. If we let H plus be 1 molar, then we'd have a pH of 0. So rather we let it be 10 to the negative 7th so that we have a pH of 7. And if we're operating in a buffered system, pH wouldn't be changing significantly. And so sort of the same thing will be set up if you have a proton transfer reaction, but I'm saying like, oh, this is all happening in the blood where it's buffered. You can go ahead and leave your H plus out of setting up your equilibrium constant. Your protons don't need to be there because 10 to the negative 7th molar for our overall sort of proton concentration and 10 to the negative 7th molar for our standard state also goes to 1. It's sort of the same concept as above. Okay? So I encourage you, if you're maybe not following that, to reread these and think about them. You'll have all this information. After class, I'll post these.